Hi Physics 2212. Today we're going to discuss Lab 2, charges spread across a surface. In last week's lab, we used a charged piece of tape to experiment with charging an insulator and determining the magnitude and direction of the field. Now, we'll conduct the same experiment and do our analysis, treating the system as a distributed charge. For this, you need to understand field forces and using integration to calculate electric field. Our field forces include both gravity and electric force. In our system, remember that the tape has two forces acting on it, gravity and electric force. Both are inversely proportional to the square of the distance between the source of the field and the observation point. This can be seen in the equation shown. This is the equation to calculate the electric field created by a point charge, which we will use repeatedly to calculate the field created by several point charges. Gravitational force is opposing our electric force, so that the second piece of tape appears to levitate. We also have to understand distributed charges. When a charge is distributed over a surface, we can no longer use the point charge formula to calculate its electric field. Instead, we have to treat it as a sum of all of its small point charges. In the image, you can see a small bit of charge, small enough to treat as a point charge, labeled dq. If we add up the electric field created by all of these small point charges along the tape, we can more accurately estimate the electric field at our observation location. This is because the distance between our observation location and our charge changes as we move along the surface, so the electric field does as well. This is the data from the last experiment and our overall estimation of charge, which we will use again as the total charge distributed across the surface. This is an image of the experiment and the tape levitating about 2.5 centimeters apart. We use this data in a GlowScript model to break the electric field down into very small pieces as seen by the small purple arrows in the image. The net gravitational and electric forces are shown with yellow and orange arrows opposing each other. This method allowed us to more accurately calculate the electric field that was creating a force and levitating the tape. As you can see, the magnitude of the electric force and gravitational force were almost identical. In our GlowScript model, we used the same formula as last lab to calculate the electric field created by a point charge. The line charge function takes in a charge and spreads it out over an even number of point charges, making all of our small dq's. From there, we looped through each top charge and bottom charge in order to calculate the field and therefore the force at each point. The sum of all of the forces resulted in the total magnitude of the electric force. In conclusion, the estimated charge on the pieces of tape are approximately negative 3.614 times 10 to the negative 6 newtons, as calculated in the last lab, and we used this to calculate the force, which is about 7 times 10 to the negative 6 newtons, in direct opposition to gravity. The assumptions that we made when we did this were ignoring air resistance on the tape as it was being pushed up, and ignoring the variability of charge, assuming it was all spread in the same place. In reality, the charges are moving in response to other stimulus. So, what if we had considered the tape as a point charge? In that case, we would have gotten an estimate for the charge that's actually smaller than what it really is. This is because the distance between the observation point and all of the charge is smaller. In reality, as we go farther away from the center of the tape, the distances between the charge and the observation location get longer. This means that there's really a smaller charge than what appears if we treated it as a point charge. Why do these values differ? Which is closer to reality? The distributed charge model is more accurate because it takes into account the differences in distance between the observation point and all of the charges on the surface. When assuming something is a point charge, it assumes all of the charge is concentrated in one area, and the difference in the distance isn't accounted for. Thank you, and see you next lab.